My name is Trent Greer, and this is my presentation on counter-fuzzing, fuzzing detection, and relevant slowdown techniques. So the importance of counter-fuzzing is basically to counter the finding of exploits. Zero-day exploits are exploits that are found, but the person responsible for mitigating those exploits are not aware. These cause a rise in attack in software. In 2014, the RAND Corporation's National Security Research Division estimated that after the disclosure of zero-day exploits, the number of attacks on a software distribution increases somewhere between 2 to 100,000 times, and the number of malware programs that exploit the vulnerability increases between 185 to 85,000 times. These zero-day exploits are very valuable, sometimes going for over $100,000 on popular software. For example, for software like Firefox or Chrome used by millions of users, they can go from anywhere between $500 and $250,000. One way to find these zero-day exploits is through fuzzing. So naturally, software developers have a vested interest in countering fuzzing done by malicious actors. Fuzzing has legitimate research purposes, such as patching exploits before a software distribution goes live. But we want to stop malicious actors from being able to fuzz our software. The size of the global security and vulnerability management market is projected to reach a valuation of $18.7 billion by 2026, showing how widespread this problem is and showing how software developers would have an interest in preventing fuzzing. So fuzzing is automated software testing to find vulnerabilities. So it tests a set of inputs against a given software. It then mutates successful inputs to retest against the software again. So starting off, looking at basic fuzzing algorithms, you're going to start with a set of input files. These would just be, if you're doing JSON, they'd be set input JSON files or something like that. The input files are then put into the executable being fuzzed, and the fuzzer analyzes the code coverage that the input files hit. So an input file here might go down the right path, another input file might go down the left path. So after the input files are put through the executable file, if there is no new code coverage, an input file is discarded. If there is a crash or a hang or a vulnerability discovered by the input file, the fuzzer will save the file and then mutate the file for further testing. The same thing happens if there is new code coverage, because that allows the fuzzer to look at other code that has previously not been hit. Some ways fuzzing mutates inputs is bit/byte flipping. It might take one bit or multiple bits and flip them or change them. So with a JSON file, this might be changing A to B or C to D in a string or something like that. You can also insert data or delete data, and data might be those typically known to cause errors, like out of bounds data, string termination data, trying for buffer overflow attacks, stuff like that. It also might randomize data input just to see if it can find vulnerabilities not disclosed through the traditional input files or mutated input files. So some fuzzing definitions that are relevant for this paper that we'll be looking at to analyze are counter-fuzzing techniques. Are executions done? This is the number of test cases ran by the fuzzer. And then obviously executions done per second is how many executions are done per second. Paths found is unique paths found by the fuzzer. This is talking about code coverage, sort of how we had the graph earlier, and it can go down different paths. Paths favored is paths that will be explored more, paths that increase code coverage and will continue to be mutated and tested again. And then the bitmap coverage is simply just code covered by the test. And then stability is a percentage of how often test cases trigger the same parts of a program. So basic solutions to counter-fuzzing are implementing timeout-inducing code. For this class specifically, that was one of the goals, was to implement timeout-inducing code. You could also implement junk code paths. This would mess with the code coverage the fuzzer finds. So it might find more code coverage in a junk path and continue to search down that junk path and waste time. You can also implement randomized execution when fuzzing is occurring. So certain things execute at certain times. Again, this would mess with the code coverage that the fuzzer sees is happening. So there are a few ways that we can detect if fuzzing is occurring. The first is to look at input metadata, timestamps, file name, file size, things of that nature. We could also look at the input data itself, validate that it's good input data, and validate if it follows a certain format that fuzzers follow. And then we can also look at the system conditions of the fuzzer running on the machine and detect if there's something that would indicate a fuzzer is running. So using input metadata, we can look at something like the file name. For example, the popular fuzzer American Fuzzy Lop always uses the same file name. It uses .cur/_ input. So if it's using the same file name over and over and over in succession, it is likely or possible that fuzzing is occurring. Fuzzing might also follow a pattern. For example, it might be test1, test2, test3, ect. File modification time is another method. If files are being modified or created and then immediately put into our fuzzer, there's potential that fuzzing is occurring. We also look at file size. So the same file size being repeated, like we discussed, bits or bytes might be flipped. So it would maintain the same file size. If there's a certain number of file sizes that keep showing up or the same exact file size every time, it could be an indication that fuzzing is happening. So file name detection, we already went over this. Small differences in file name, exact same file name, or file names typically used by fuzzers. Like American Fuzzy Lop, again, uses the same file name every single time. So if take the set of popular fuzzer file names and input that, we can potentially detect if fuzzing is occurring. We can also look at file timestamp detection. So as stated before, modifying a small time period before execution, creating a small time period before execution, or if there's a pattern in file time execution, let's say 10 milliseconds between the creation of each file, it could be an indication fuzzing is occurring. Also, file size detection. Like we'll discuss earlier, the bit flips could add or subtract 1 byte. If the fuzzer is randomly mutating our files by adding new bytes, new characters, new data, if it adds a new character, it's going to add 1 byte. Or if it removes a new character or an old character, it's going to add 1 byte. And then again, the same file sizes set being used over and over and over. And then for input data, it could be not properly formatted. For example, a JSON file should have an even number of quotation marks. So perhaps we could terminate the program or detect fuzzing is occurring by looking at the number of quotation marks. We can also look in other ways, if it follows the same format, like colons, things of that nature, brackets. If it contains unusual characters or strings, so if it contains like string termination characters, max integer, minimum integer, things like that, or if it contains the same data as previous files. If we're running this somewhere and we can save the file and analyze it against and 1 bit is changed or 1 byte is changed, that might be an indication of fuzzing. So we can also look at our system conditions. So American Fuzzy Lop, for example, creates a fork server. This is so it can test multiple inputs at the same time. And if it's a program that should not be run in simultaneous execution, then you could use this as a way to know fuzzing is occurring. This method is generally slow to detect if a program's been forked, or if there's a fuzzer program running, such as American Fuzzy Lop. You know the executable name, executable names of other popular fuzzers. There's potential for fuzzing. Or if it's running in a virtual machine, a lot of fuzzing takes place in a controlled environment. The malicious actor would have some reason to put in a controlled environment so that they can reproduce results, reproduce vulnerabilities. The system conditions would always be the same, things of that nature. So if we put it all together, one indicator does not necessarily mean fuzzing is occurring. There's legitimate reasons to use the same file over and over. If you keep misformatting it or something, and the file name remains the same, or you just change one or two numbers. So we want to try not to disrupt non-malicious use. So these things should be considered. And it's up to the programmer on what conditions work for their program to understand if fuzzing is occurring. So this paper and presentation explores three counter-fuzzing techniques. One is a very simplistic approach. One is a randomized jump approach, and another is a randomly executed code approach. So the simplistic approach is to first check for fuzzing conditions that are previously mentioned. Then you put a loop calling sleep. The reason it loops instead of putting a large value for sleep is that fuzzers usually start off using test cases to see if fuzzing is viable. So if sleep is called for like 20 seconds, it could fail one of those test cases, and it would immediately alert the fuzzer that something suspicious is occurring, that counter-fuzzing is occurring, and then the sleep argument gets tested again and again for the fuzzer, slows down execution speed. So a simple example of this is having this loop. The reason sleep 0.9 was chosen was that American Fuzzy Lop will time out if it is 1 second, if an execution of a instruction takes more than 1 second or more. And the reason 300 was to, again, prevent timeout. I think it times out at a little under a certain number for executions in a program, so execution per second. And this was the minimum that seemed to work without timing out American Fuzzy Lop. The benefits to implementing this simplistic approach is that it's super generic, it's easily insertable, there's an extreme slowdown of fuzzing. Of course, this is dependent on how many times you're calling sleep and how many times your loop is looping. It's input independent too, so this could work on a JSON file, it could work on a text file, it could work on anything. There's a lot of cons to this though. The simplistic approach is easily detectable. So if you put this in Ghidra or something, or you call a command to look at the system calls, you can see that sleep is occurring. And not only is sleep occurring, it's occurring multiple hundreds of times. So that's a pretty big indicator that there's some counter-fuzzing going on. We ended up testing CJSON in this program. So CJSON program like that should not have any sleep statements. So that's a pretty big indicator that something is going on. It's easily counterable. The sleep call can be hooked, and someone could essentially make the argument do nothing. They could make the sleep just be a no operation, just instruction, and just completely skip over it, just completely go around your counter-fuzzing efforts. It also does not reduce code coverage. The fuzzer follows the same execution, it just follows it in a slower manner. So once it's out of that sleep loop, it'll continue fuzzing as normal. The inputs will be the same, the mutated inputs will be the same, and it'll hit the same code blocks as if fuzzing was not occurring, just at a slower rate. The second method we analyzed was the randomized jumps approach. It implements jump labels all over a program. So you detect fuzzing conditions as well, generate a random number, and then jump to labels based on the number generated. So here's an example of that code. First, you generate a random number. Depending on your number of cases, will be your what you're modding it by, and then you have a switch statement, and so the number will go in there, go to a case, and then go to a label. So the labels are programmer defined, and so you can place labels anywhere in your code, but you have to be careful about where you place them. So this is a visualization of the randomized jumps method. So first you'd have a input file like test1.txt. It get inputted into the program and then go to your fuzzing detection code. And then let's say your mod statement, your jump statements, it goes back. You have a jump statement at the top of the program. So potentially it hits that jump statement, goes back to the top of the program, and then it would go back down into your randomized jump again. And then it could hit another code path. Let's say it goes down here on the left and hits code path 2. Now let's look at the same input. And because it's random, it gets inputted, hits those switch statements and jump statements, and then goes to a different code path. It only does one randomized jump this time. This is a very simplistic overview. You could have multiple jump statements that could jump all over the place, more than 2. This would extremely mess with code coverage. So the implementation benefits are potential loops, which will cause slowdown. It will take more time to execute your program than it normally would. It's built-in obfuscation too. If you're doing some software reverse engineering and looking at the code under a program like Ghidra, you'll have to follow these jumps, see where they're going, see why they're occurring. It breaks fuzzing code coverage. So code that shouldn't hit a part of the program, or inputs that shouldn't hit a part of the program, do, and they don't do it consistently. So it might go one way one time, one way the other, as demonstrated. That makes it hard to replicate inputs generating vulnerabilities. So all those files that your fuzzer is saving as generating vulnerabilities, they're essentially null unless you can replicate them. And it's not as easily detectable. Rand would have some uses in programs, even simple programs, maybe not see JSON, but sleep is a pretty big red flag. I would say Rand is not. Here are some cons to the implementing randomized jumps. The Rand system call can still be hooked like sleep. Just because it's not as obvious doesn't mean it can't be hooked. So someone could use it to generate the same number every time, depending on where they want to go in the program. It relies on programmer implementation to not be ineffective. You need to put the jumps in places that aren't going to totally break your program or cause more vulnerabilities. So the programmer needs to be extra careful about that. With the simplistic approach, you can pretty much just put that in there and be good to go. But the programmer needs to decide how many jumps to put, where to put them, things like that. It could be detected via fuzzer stability. We talked about stability as the same way as a way of measuring how much an input is hitting the same parts of the program consistently. And so fuzzer stability on this method is going to be really, really low. So a simple program like CJSON, if it has low fuzzer stability, that means either the program is broken to begin with, which a would-be fuzzer is going to assume that's not likely the case, or that there's some counter-fuzzing happening to dissuade malicious actors. And the slowdown is not as pronounced as a simplistic method. That's just the nature of it. It's not calling any sleep calls. It's not looping through them. So it's not going to slow down as much, but it will induce a slowdown and timeouts. So the randomly executed code method is a method that uses a switch statement to randomly execute code. This is implemented in a similar way as the randomized jumps method. The code is programmer defined, so one can put other counter-fuzzing methods in their switch statement. And again, the programmer needs to be careful about what they put there if they want the counter-fuzzing to actually be effective against fuzzers. So here's an example of randomly executed code. So again, there's this random number being generated and modded by the number of cases. And there's a switch statement, which puts on a case, and then the programmer defined code is in there. So that could be anything. It could be code that doesn't do anything. It could be junk code. It could be code that does jump around the program. It could be terminating the program, stuff like that. So here are some benefits to the randomly executed code implementation. The randomly executed code doesn't jump through code, which could potentially produce unexpected results in the same way that the randomized jumps method does this. The programmer chooses the slowdown code. They can choose what is acceptable for their program in order to prevent counterfuzzing, and there's potential for a large slowdown depending on what code they implement. The randomly executed code also helps maintain a greater stability for a fuzzer, so as to not alert a malicious actor that something is taking place. It's not jumping all over the program. It's a small subset of conditionals that either get hit or do not get hit. It doesn't take up a large part of the program, hitting multiple instructions. There's potential for obfuscation. Someone could return early out of the program, exit early out of it, and mess up a test case for a fuzzer. And it also reduces bitmap coverage simply because there's more conditionals and potential for those conditionals to be hit. Some implementation cons are, like the randomized jump method, RAN can be hooked to always produce the same number or to produce a set of numbers. It limits path execution. It's not looping anywhere. And slowdown code and number of conditionals is program defined. This was also listed as a pro, but it's a con here because there's not inherent slowdown code. The programmer has to make sure the slowdown code they are using is viable. Testing these programs was done on a 12th gen Intel Core i7 2.7 gigahertz processor. It was run on a virtual machine, which was allocated 4 gigabytes of RAM and 4 processor cores. The virtual machine was running a 64-bit Debian 11.6.0 distribution. Each test was ran for 10 minutes. It's not an overly long amount of time, but it's enough time to get usable results. CJSON was used as our base program to implement these counter-fuzzing techniques, and it was tested against American Fuzzy Lot version 2.52b. So here are our baseline statistics. You can see they're pretty high. The execs done is 3.8 million. The execs per second is 7,000. There are 628 total paths, 95 favored paths, 614 paths found, and 1.29% bitmap coverage with 100% stability. So if we look at the simplistic approach, the execs done dramatically reduces from 3.8 million to 1,000, with the execs per second being 1.84, which is also dramatically reduced from 7,000. Paths total, again, reduced by 550. Paths favored and paths found reduced by similar amounts. I think paths favored was 95 and now it's 9. Bitmap coverage reduced a little bit by 0.3%, and stability was maintained. So for our randomized jump testing, we placed 6 jumps throughout the program. Some were above the fuzzing detection methods, some were below, some were in it. And their place of points is not to cause code errors. This was discussed. If a programmer causes code errors, they could unintentionally create vulnerabilities. And so analyzing these results, it's not as a dramatic of an improvement. The execs done was reduced by around 2 million. The execs per second was reduced to 534 from 7,000. Pass total was reduced by around 500, a little over 500. Pass favored and pass founds also reduced. Bitmap coverage was reduced more than the simplistic approach, and it was reduced by about 0.5% from our baseline. And the stability is a huge problem. It was reduced down to 27.15. For a simple program like CJSON, this is a indicator that something is wrong to a malicious actor. And there's 14.6 thousand timeouts. That is likely due to where the jump code was placed instead of just having the method there itself. So to test our randomly executed code method, we had 5 switch statements that are randomly hit. The first is just a simplistic print statement. It just prints hello world. The second is a sleep statement that just calls it 1.9. This was done to demonstrate how the randomly executed code could be used to implement other slowdown methods. The third case returns and simply terminates the program. It returns a successful JSON parsed code, even though it should return a failure code. The fourth case modifies the given input. It takes the JSON inputted into the file and makes it null and lets program execution continue. And then the fifth case just simply continues program execution as normal. So looking at these results, they're better than every other results we've had. The exec stun is 2.7 million. The execs per second is 6,000. That's not a decrease per se of a lot. That's about 1 million for the exec stun, and about 700 for execs per second. This is good because it doesn't tip off a malicious actor that counter-fuzzing is occurring. Someone would expect CJSON specifically to run relatively quickly. And so if it's only running 1,000 times, then in 10 minutes, it's pretty obvious that something is going on. The pass total was also the lowest we have from our results of 17. Same with pass favored and pass found. In 10 minutes, it only favored 4 pass and found 3. The bitmap coverage was also reduced by a ton, 1.25 from the baseline. Sits at 0.03%. The stability remains at 100%, meaning it's, again, not tipping off a malicious actor that something's happening. The timeouts are the same way. They're relatively low at 23. So it's not easily detectable. It's easily insertable, but again, it's reliant on the programmer to place the right slowdown code in their executable. So in conclusion, several fuzzing detection methods were evaluated. It is recommended that these methods are carefully implemented by a programmer and not just lazily put in there, as it might affect a legitimate user. Also, several of these methods should be used with one another to make sure legitimate users are not affected. 3 counter-fuzzing techniques were also evaluated: the simplistic approach, the randomized jumps, and randomly executed code. We found that randomly executed code is the most useful and is the recommended approach. This is because it has low detectability. Its stats are somewhat in line with the baseline, which makes it not detectable. It slows down the number of paths found, total pass and pass favored, even more than the simplistic approach and more than the randomized jump approach. It maintains stability consistent with the baseline. And then the simplistic approach is the least useful because of its detectability and its counterability. One can just hook a sleep statement and essentially make it useless. That concludes my presentation on counterfuzzing. Thank you for listening.